Traditional mechanical engineering relies on the assumption of material uniformity. When you apply a uniform tensile load to a standard block of steel, it necks symmetrically and snaps cleanly. Because steel is isotropic, its mechanical properties are identical in every direction. Defining its entire mechanical identity only requires two scalar values, Young's modulus and Poisson's ratio. Advanced carbon fiber reinforced polymers and other composites operate outside of this mathematical simplicity. When loaded off-axis, a composite panel violently twists and shears, splintering asymmetrically along its internal diagonal lines. These materials are engineered to be orthotropic or anisotropic, meaning their stiffness and strength are highly directional. To design advanced structures, engineers must move past scalar Hooke's law and calculate the material's mathematics from the ground up. Our model begins at the micro level with the behavior of a single microscopic ply. We then scale these equations upward through rotational transformations and interactive failure criteria. In composite engineering, the structural design is the material's underlying mathematics. We start at the micro level by defining the unidirectional lamina. In this 3D coordinate system, axis 1 strictly aligns with the internal fibers, while axis 2 represents the transverse direction. Because the lamina is thin, we apply the plane stress assumption, treating out-of-plane stress along axis 3 as 0. This expands Hooke's law into a matrix equation connecting the stress and strain vectors. The longitudinal modulus, or E1, defines the stiffness along the high-strength fibers. The transverse modulus, E2, measures the weaker stiffness of the resin matrix holding those fibers together. The final independent constants are the shear modulus and Poisson's ratio. This completed grid is the reduced stiffness matrix, or the Q matrix. Defining the baseline stiffness of a single composite layer requires evaluating these four directional constants simultaneously. In real-world structures, applied loads rarely align perfectly with the internal fiber axis. We must rotate the local stiffness matrix into a global XY coordinate system using an angle, theta. Applying transformation matrices converts the local Q matrix into a global structural matrix. This transformation introduces the 1,6 and 2,6 terms, which do not exist in isotropic materials. In physics, these variables represent extension-shear coupling. Physically, this means a straight pulling force causes the material to twist and shear off-axis. Engineers must mathematically predict this behavior to avoid design failure. Once we calculate stiffness, we must determine the limits of strength and failure. Traditional yield criteria, like the von Mises theory used for metals, are inaccurate for composites. This graph represents a basic maximum stress criterion. It checks tension and compression limits on each axis independently, forming a rigid rectangular boundary. This model fails because it ignores how stresses in different directions interact with and weaken the material. The industry standard is the Tai-Wu failure criterion. Tai-Wu evaluates a quadratic polynomial of the stress state, combining longitudinal, transverse, and shear stresses into a single interactive boundary. A stress scenario that the old model would pass as safe is clearly identified as a failure point by the Tai-Wu envelope. Ignoring how multi-axial stresses interact directly leads to structural failures. Interactive models like Tai-Wu are a technical necessity. Engineers build macro-scale components by stacking single laminae at alternating angles. In a typical stacking sequence, layers are oriented at 0, 45, -45, and 90 degrees to form a thick, unified plate. We rely on Mindlin plate theory to calculate the physical bending of these multi-layered structures. Classical theories assume that flat planes stay perfectly flat under bending, but composites do not follow this rule. Composites have very low out-of-plane shear moduli. When bent, they undergo transverse shear deformation, where internal vertical planes angle significantly. To correct for this in finite element software, engineers apply a shear correction factor, commonly 5/6, to the stiffness matrices. Correcting for transverse shear deformation is the final bridge required to accurately model macro-scale structures in simulation software. These theories are the foundation of extreme industrial and aerospace engineering. Current research in the field integrates these anisotropic failure envelopes and stiffness matrices to solve dynamic problems. Analyzing the dynamic aerodynamic loading of stiffened piezoelectric plates is only possible because our FEM solvers are built on this rigorous anisotropic math. In composite engineering, the structural design is the material's underlying mathematics.